sky never lied and brought me to the dark. One by one into the fire.
Our knowledge of the universe has grown rapidly in recent years. But what scientists can actually observe and prove with certainty makes up only a tiny fraction of the cosmos. The universe is filled with mysteries, dark matter and dark energy. Whatever it may involve, these unknown variables dominate the structure of space and the development of the universe. Dark matter and dark energy seem to surround and permeate us everywhere. Now, researchers around the world are working to shed light on the dark side of the universe.
What is our universe made of? Well, first of all, everything surrounding us. But this accounts for only a little less than 5%. And this is called standard matter. 5 times more mass is the so-called dark matter. And it's called dark because you just can't see it. The large remainder, namely 72%, is what is known as dark energy. You can't see energy anyway, but dark means we don't know where it comes from, nor, more importantly, what it actually is. So, what can we see of the universe? Well, everything that emits light and is visible. In other words, we cannot see most of the universe, namely 95% of its contents. And we have only known all of this for a little more than 20 years.
All life, atoms, planets, stars, and galaxies make up just 5% of all substances that exist in the universe. This startling insight comes from cosmological observations. A much larger portion, around 23%, consists of something known as dark matter. Our galaxy, the Milky Way, is also surrounded and permeated by a large accumulation of dark matter. And it is this dark matter that has played a decisive role in the development of our galaxy. To this day, however, its true nature remains a mystery. Cosmologists are convinced that dark matter really does exist. But until researchers can unlock its secret, they cannot answer the fundamental question of what the universe is made of.
That is actually the mystery. Of course, we know that we can't see everything in the universe. If you lose your shoe in space, no one will find it. And then you could say your shoe is also dark matter because you can't see the matter. But we know that this dark matter, which we can feel and detect everywhere through its gravitation, cannot be made of the same material as your shoe. It is referred to as the baryonic matter. But that is a matter whose nature we are not familiar with, and that has not emerged from atoms. And that makes it exciting, because there is so much of it. We know that a world exists about which we still don't know anything at all.
The Swiss astronomer and physicist Fritz Zwicky is considered the father of dark matter. As a young researcher with an American research grant, in the mid-1920s he relocated to a stronghold of astronomy, the California Institute of Technology, Caltech, in Pasadena near Los Angeles. With a reputation for being a curmudgeon, Zwicky first complained about the lack of mountains he had been promised there, but then he got down to work. In Zwicky's day, Caltech in Pasadena was already making groundbreaking discoveries in the investigation of the universe. Edwin Hubble, who also worked there, demonstrated that our galaxy is just one of countless others throughout the universe, and that these galaxies are all moving away from each other. With this, Edwin Hubble had discovered the expansion of the universe, the foundation for the Big Bang theory. The object of Fritz Zwicky's observations was the Coma cluster, which consists of hundreds of galaxies. He was surprised to realize that, relative to their gravitational effect, the speeds of the individual galaxies were far too high, and that they should actually be expected to break free of the cluster. He postulated that there must be some unknown, invisible mass keeping the galaxies in the cluster. This was the birth of the idea of dark matter.
Fritz Zwicky determined that we need dark matter, matter we can't see, to explain the measured rotation curves. The problem with these measurements is that you have to make lots of astrophysical assumptions, and the measurement itself is not that simple. Nowadays, we have lots more observations that allow us to conclude that dark matter must exist.
Zwicky published the results of his research in 1933 and was ignored. However, he was not the first to suspect that there was mass missing in the universe. At nearly the same time, the Dutch astronomer Jan Hendrik Oort speculated about the existence of nebulous invisible matter. This was how he explained the gravitational anomaly, the unexpected results obtained when measuring the speed of stars in our Milky Way. But it was only decades later that the theory was scientifically recognized and became part of the standard cosmological model.
Fritz
Zwicky was no ordinary scientist either. He often got into arguments with others. And then people just said, "Oh, Fritz, leave him alone. He's got another nutty idea." But he was right.
The most modern astronomical instruments of their day and his methodology helped Fritz Zwicky gain new insight into our universe. It was not something he had been specifically looking for, rather more of a scientific coincidence. But his discovery did not fit the prevailing views of the Astronomical Society at the time. It was then the astronomer Vera Rubin who proved that Fritz Zwicky was right. She analyzed the orbital velocities of stars in distant galaxies, and these orbital velocities were also far too high for the total masses of the galaxies observed. The astronomer was familiar with Fritz Zwicky's work, along with the rejection he had experienced. But Vera Rubin was persistent in pointing out the missing mass that her investigations identified. Because her observations and calculations were straightforward and irrefutable, the existence of dark matter was actually taken seriously for the first time in the history of astronomy. But Vera Rubin's groundbreaking research also went largely unappreciated during her lifetime.
Vera
Rubin was a woman, and women had an extremely difficult time back then. She looked at the outer areas of the galaxies because in areas where you can see everything, the gentlemen had already addressed those. Nobody was interested in the outlying areas. She found that the galaxies rotate much faster than they should, which means that there is this additional dark matter in the outlying areas that you can't see. At first, people didn't really believe her, but then she found so many galaxies that there was no way to refute it anymore. She ultimately became very famous and well-known.
The second great unknown in cosmology is an even more puzzling substance: dark energy. Researchers suspect that this is what has been increasingly driving our universe apart for the past 5 billion years. This is an unexpected phenomenon, as the gravitational pull of the matter in the universe should actually be slowing down the expansion of space. This slowing effect of gravitational forces was still believed just a few decades ago. Measuring the distances of foreign galaxies from our Milky Way was supposed to prove this theory, but cosmologists were surprised at what they discovered. Rather than slowing down, the universe is expanding, and faster and faster.
Dark energy has been one of the big surprises that many theorists would rather not have had, because, in a certain sense, it's actually an even bigger puzzle than dark matter. Dark energy is a kind of force field, you could say, or an effect that runs counter to the normal effect of gravity. It's actually a huge mystery.
Why do the stars at the edge of spiral galaxies orbit around their center at high speed rather than fly out of orbit? What holds the universe together, and what makes it expand faster and faster at the same time? The terms dark energy and dark matter ultimately also reflect the current state of research. In both cases, dark is also synonymous with unknown, or put more simply, we don't know. Astronomers can register the effects of these mysterious forces, but they still do not comprehend their nature. The existence of another phenomenon of the dark universe was also long disputed: black holes, supermassive objects that still pose many mysteries. Black holes cannot be seen directly, but what goes on inside them is beyond our imagination. These are fascinating objects in which the standard physics we're familiar with no longer seems to play a role.
Black holes are very interesting because, on the one hand, we now have a clear sense of how they affect their surroundings. On the other hand, all the details of the inner workings remain hidden from us behind what is referred to as an event horizon. Physicists actually say that this is why this inner part no longer belongs to our universe, a kind of parallel universe. Why do we still understand so little about black holes at the moment? There are two reasons for this. One is that all known black holes except for one, namely in the center of our Milky Way, are millions of light years away. And that's why we can't see any details with our telescopes. The second is that because black holes rotate incredibly fast, their behavior is rather complicated.
A black hole was captured in an image for the first time in 2019. In fact, the black hole itself is not visible in the image. Like dark matter, black holes cannot be seen directly. They only give themselves away through their enormous gravitational pull. What is visible, however, is the glow of matter as it tumbles into the black hole.
So it was a shot like the portal to hell. This abyss, the black hole, has incredibly destructive properties too, and can swallow up everything. And in this picture with the glowing gas around the black hole, which actually casts a kind of shadow on this accretion disk, this was the first time we had a tangible, visible image of a black hole that was actually in the process of interacting with matter. That really did fascinate me, because for many years, I hadn't thought that something like that was even possible.
There have been indications of the existence of black holes for a long time. But it was only the combination of 7 radio telescopes distributed around the globe, the Event Horizon Telescope, that permitted a level of detail that made imaging possible. Researchers were also able to use the array to create an image of Sagittarius A star, the supermassive black hole at the center of our Milky Way. The black holes captured in the images are gigantic, which is the only reason why their shadows can be observed at all with the telescopes currently available. The smallest black holes known to date are stellar black holes. They can form when stars that are at least 3 times as massive as our Sun collapse. Black holes that are even smaller than these, with less than 1 solar mass, are theoretically possible. But given what we currently know about stellar evolution, they cannot be created in supernova explosions. If such small black holes actually do exist, then they could well be related to dark matter. And then there is another theory based on an idea by the British physicist Stephen Hawking. According to this theory, black holes may have been created immediately after the Big Bang, so-called primordial black holes. Hawking hypothesized that their potentially large number and distribution in the expanding universe might explain the phenomenon of dark matter. According to his theory, such miniature black holes could have been captured by stars. These persistent objects, known as Hawking stars, would thus have a black hole at their center.
Stars like these would first reveal themselves through unusual properties. And as far as I know, no convincing candidates have yet been found to suggest that such a thing actually exists.
Primordial black holes, created in the early universe, would be an elegant solution to the problem of dark matter. The unknown mass would consist not of still unknown particles, but of countless mini black holes distributed throughout the universe.
A primordial black hole is a black hole that's existed since the beginning of the universe. And of course, we can't observe a black hole directly. That would make it a great candidate for dark matter. But we know that the number of primordial black holes, as far as we understand them today, is not high enough to account for all the dark matter we need to explain our models.
Whether such primordial black holes actually exist is still in dispute. They are a hypothesis, a theory. None has yet been found, but researchers are on the lookout. Data from the LIGO and Virgo gravitational wave observatories, for example, have been scoured for possible evidence of such mini black holes with less than one solar mass. So far, nothing has been found.
Together, dark matter and dark energy account for 95% of our universe. The two are usually referred to together, but one has nothing at all to do with the other. Dark matter has real mass, while dark energy is virtual energy, meaning that this energy cannot really be used in practice. Unfortunately, neither is directly visible with a telescope. You can only observe their effects. For example, dark matter causes galaxies to rotate rapidly, while dark energy contributes to the rate at which the universe expands. So, to better understand both, all we need to do is accurately measure galaxies' rotation rates and the speed with which they drift apart. And this is exactly the mission for the new Euclid Space Telescope.
Euclid's mission is to solve some of science's greatest mysteries. The telescope will capture and map 1/3 of the visible sky, creating the largest and most accurate three-dimensional map of the universe to date. This map will ultimately depict the positions, shapes, and movements of billions of galaxies. Euclid will gaze up to 10 billion light-years into the past, providing researchers with a kind of time-lapse record of the development of the universe. Scientists hope to use this map to make astounding discoveries about gravity, dark matter, and dark energy.
Dark matter is so fascinating, and it's really scientific. It's so profound that you just want to understand how the universe works. How? Why is it expanding so quickly? How big is it? What happens at some point after that? Will there be an end, even if it's billions and billions of years away? And how did the beginning originally come about? This also poses very powerful philosophical questions too. Religion is connected to this. Is there a God who created all this, or can it all be explained naturally? These are huge questions, and with missions like Euclid, we're getting to the bottom of those questions. We will not find God, I have to say that up front, but we are trying to figure out how the universe works.
The mission is named after Euclid of Alexandria. The Greek mathematician who lived around 300 years BCE is considered the father of geometry. The telescope is intended to show how dark matter and dark energy influence the visible cosmos and how they have contributed to the development of our universe. The researchers want to explore the geometry of our cosmos.
Euclid measures what's known as cosmic structure formation. So we're looking at how galaxies and galaxy clusters and ever larger structures have emerged over time from an originally very homogeneous universe. And the speed at which these structures emerge depends on dark matter, which wants to form structures by attracting them gravitationally, and on dark energy, which prevents this growth by expanding space further and further diluting the density of matter. And this is exactly what Euclid can measure very precisely, allowing us to draw conclusions about the accelerated expansion of the universe and dark energy.
How and why does our universe look the way it does today? This is one of the questions that Euclid aims to answer. The telescope has two cameras. One delivers high-resolution images in visible light, while the second instrument measures the near-infrared light and records both images and spectra. The researchers are already excited about the first data sets from the new telescope, including an image of the nebula Messier 78 in the constellation Orion, 1,300 light-years away. Euclid peers deep into the interior of this nebula and has discovered more than 300,000 new objects.
I expect that some Nobel Prizes will be won based on the data that Euclid will measure. Of course, I can't predict what exactly that will be. That is precisely the mystery of Euclid, to answer such questions. But I'm convinced that there really will be completely new findings here, that there will be surprises, and that we will still have no idea what those surprises might be.
But the telescope doesn't just provide wonderfully bright images. It can also detect planets that drift alone through the universe, known as rogue planets. These are objects of planetary mass that are not gravitationally bound to a star. Such rogue planets are difficult or even impossible to see, but they have been discovered over and over in the past, though never to the extent that Euclid is now detecting them. And while they may be hard to find, researchers now assume that there are several billion of these lonely nomads in our Milky Way alone. This means that they are far more common than previously assumed, but would still only make a small contribution to dark matter.
Es gibt einige Ansätze, wo man versucht, dunkle Materie durch kompakte
There are some approaches that attempt to explain dark matter on the basis of compact objects such as planets or dark stars.
die Beobachtung des
But observations of the large-scale universe and the cosmic background radiation have shown that this field, the proportion of dark matter, is not large enough to explain all dark matter.
brauchen also
So we
tatsächlich
really need something new, something that goes beyond this.
das darüber hinausgeht.
Further proof of the extraordinary capabilities of Euclid can be seen in an image of the galaxy cluster Abell 2390. More than 50,000 galaxies are visible in the image. There is also an almost perfect representation of gravitational lensing, a phenomenon in which the light from distant galaxies is bent and distorted by gravity. This offers multiple views of the same object at the same time. This lensing is used by Euclid as a key technique for exploring the dark universe.
To make distant, very faint galaxies visible, Euclid uses what is known as the gravitational lens effect, which works like this. Here is the Earth. We look from Earth to this distant, very faint galaxy. Its light then emanates from here. And let's take a beam of light that would pass by Earth in this direction. But if you put a massive galaxy right in between, then the following happens. This ray of light is bent, as Einstein says, and then goes toward Earth. And the other ray of light on the other side also meets our eye, and that means we see more light. What do we see? If we trace this ray back, our eye says the galaxy is here and here. If everything is perfectly aligned, it looks like this. Here, our galaxy, the distant one, and here, this vast galaxy is now interposed. And that creates this circular ring. As I said, everything only happens when everything lines up exactly, which of course is very rarely the case. But when it does happen, then we have the perfect mass magnifier.
Such mass magnifiers, or gravitational lenses, are an important tool for cosmologists. They provide information about the distribution of dark matter and help investigate the effects of dark energy in greater detail.
Das, was Euklid allerdings
But what
hauptsächlich
Euclid mainly measures is the weak gravitational lens effect.
Das ist der gleiche
This is the same effect, but much smaller. So you distort a circular galaxy by 1% or 2%, for example.
1%.
This is impossible to see with the naked eye, of course. But if you calculate over many galaxies, you can actually tease out this small percentage from the data.
Diese paar Prozent aus den Daten
And
herauskitzeln.
this is where Euclid is very
Hier
important,
ist Euklid sehr
because
wichtig.
for the first time, we'll be measuring galaxy distortion for several billion galaxies with unprecedented precision.
Damit eben eine nie dagewesene Genauigkeit erreichen werden.
Astronomers can only characterize dark matter on the basis of gravity. After the Big Bang, all that existed was hydrogen and dark matter. To start with, the dominant dark matter was not evenly distributed in space, and first condensed into extended mass structures. Attracted by these structures, hydrogen flowed in and clumped together to form stars and galaxies. So stars and dark masses are concentrated in certain areas of space. Areas with a lower mass are left behind. One result of this uneven distribution is the current structure of our cosmos. This is how dark matter created and continues to determine the large-scale structure of the universe. Researchers can visualize its distribution in computer models, where the mysterious force becomes visible in simulations of the formation of the cosmic structure, for example. It forms a delicately spun web of matter, a large-scale structure consisting of galaxies and gas, formed and determined by dark matter.
It's like a piece of Swiss cheese. There's a highly structured universe today, and the overdense regions that we see as filaments and as a cosmic web have to be offset by areas where the matter is no longer there. So it's just been redistributed. That's why there are these large regions where the density is very, very low, which are almost empty, but not completely empty.
The data Euclid provides should permit even more precise conclusions about the distribution of dark matter in the universe, and about how it influences the shape and distribution of galaxies in the cosmic web. Researchers are relying on Euclid to capture large areas of the night sky and reveal more about the distribution of galaxies.
We're trying to build a kind of digital twin of the real universe on the computer, because the statistical power of these observations is so great that we also need theoretical models that have similar explanatory statistical power. And the only way to achieve this is to make large computer simulations that predict a sufficient number of galaxies so that we can make exactly the same measurements in the computer simulation, in the digital twin of our real universe, as made by the Euclid satellite. This means, for example, that systematic observational errors can be precisely narrowed down and calculated out. And that's the mission behind creating such theoretical twins, which we can then use to evaluate the data in the best possible way.
Dark energy influences the speed at which the universe expands. If the rate of expansion of the universe at different times can be determined, it is possible to deduce how strong the effect of dark energy was in these phases. In 1929, the astronomer Edwin Hubble discovered that the farther away any given galaxy is from us, the faster it is moving away from us. He concluded that the universe as such is expanding, thus confirming the Big Bang theory postulated by the priest and astronomer Georges Lemaitre. Hubble's discovery unleashed an earthquake in the cosmological order assumed at the time. Even Albert Einstein thought the universe was static. So the universe apparently has a beginning, an origin. From there, it has continued to expand. Matter is distributed throughout ever-expanding space.
If something is drifting apart, then there must have been a starting point. Then you can calculate the whole thing back to a single point. And even Einstein didn't want that. He always thought that although there was the general theory of relativity which would explain the expansion of the universe, he always believed that the universe had always existed and would exist forever. And the fact that the universe had a beginning, possibly without anything preceding it, didn't appeal to him at all.
In the late 1990s, a new method began to be used to measure the rate of expansion of the universe. Researchers were guided by the uniform luminosity of thermonuclear supernovae, exploding white dwarf stars. Their mapping produced a surprising result. The expansion of the universe is accelerating. In 2011, astrophysicists Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for this discovery. To this day, the mysterious force that is driving the cosmos apart ever faster is still unclear. Current measurements suggest that nearly 70% of the total energy of the universe, masses included, consists of dark energy, which could generate this force. Einstein's cosmological constant, possibly caused by dark energy, suddenly made sense again. It allowed the adaptation of theoretical models to observations.
You have
a cosmological constant that even predicts such an accelerated expansion of space, which is amazing. The laws of general relativity already predict this. Like a treasure chest you can open, and there you can see things you can't understand, things that were discovered before we could understand them. So maybe it would be better to have found dark energy 100 years from now. Then we wouldn't have to make such an effort now, because our physics isn't ready to understand it yet.
The most coherent attempt to explain dark energy to date is that it involves what is known as vacuum energy. This is energy caused by so-called virtual particles found throughout the vacuum. Virtual because they are created momentarily as particle pairs and immediately disappear again, which is why they cannot carry any real energy. Their constant creation and immediate disappearance correspond to non-usable, that is, virtual energy, so-called vacuum energy. But these particle fluctuations generate a real force that causes the vacuum to expand. The more vacuum is created by expansion, the more virtual particles there are, and so the expansion force constantly increases, leading to an accelerated, expanding universe. A possible explanation for how dark energy causes the universe to expand at an accelerated rate.
Meanwhile, the entire universe can only be constructed as an intermediate space, devoid of matter. And then this space itself has certain properties. For example, that it can expand. Einstein demonstrated this. Space can be curved even if there is no matter in it at all. At first, it was inconceivable to think of a vacuum as a physical object. What we are now discovering in quantum mechanics is that the vacuum not only has more properties than just being inherently curved, or having other geometric properties, but that new things can emerge from the vacuum.
Dark energy and dark matter. These are the two great unknowns in the equation of the universe. The existence of dark matter is viewed as a verified scientific truth. But despite decades of research, it is still not known what this invisible mass in the universe actually consists of.
So, what is dark matter? One leading theory says it's a special kind of elementary particle called a WIMP. WIMPs are weakly interacting massive particles. There are two favorites, known as neutralinos and axions. And you immediately notice from the words, oh, that's something pretty weird. Yeah, that's true. And that's why we haven't seen them yet. But let's assume that dark mass consists of these special particles. What would that mean? Let me show you with this fountain pen. Why can I hold this fountain pen now? Because my fingertips interact with the surface of this fountain pen electrically. And that's why I can touch it. Now let's assume that it was made of dark matter, and I tried to grab it again. Then the following would happen. I wouldn't be able to grab it at all. My hand would pass through the dark matter because it cannot interact. That's what constitutes dark matter. And you can see right away that it must be incredibly difficult to detect.
Over the years, lots of possible candidates have been proposed to explain dark matter. Elementary particle physics has achieved a great deal, but the picture is apparently still incomplete. To this day, no suitable particles for dark matter can be found in the standard model.
It's like looking for an earring in a big house. You know you've lost the earring in the house and you have 300 square meters, maybe even with a really thick carpet. So that's fun. It takes days to find it. Either you give up at some point and say, okay, the earring doesn't matter to me anymore, or you end up scanning every centimeter trying to find that earring. And that's the situation we're in now. It's not that the physicists are just looking anywhere in the void. They know exactly where to look, and they're trying hard. We'll have to continue this work over the next few decades, and then we'll see. But I absolutely want to find the earring.
Expectations were high for the latest expansion stage of the world's largest particle accelerator, located underground around Lake Geneva, Switzerland. The LHC, the Large Hadron Collider at the European Organization for Nuclear Research, CERN, was designed to track down the particles that make up this mysterious matter. So far, nothing has been found. The physicists named one of their favorite theories SUSY, an abbreviation for supersymmetry. Simply put, for every known particle, there should be a corresponding counterpart in another hypothetical particle world. The lightest of these supersymmetric particles would not be able to decay any further and would thus be persistent and could represent dark matter, according to the theory. But even particles like these have not yet been detected. The existence of the Higgs particle was predicted by Peter Higgs in 1964. When it was successfully detected in 2012, it seemed to mark the dawn of a new era for particle physics. Everything seemed possible, if only the particle accelerator was big enough. Then a certain disillusionment set in. Many of the predicted particles simply cannot be found.
The only thing we know for sure is that there's a vast amount of mysterious matter. We know that from observations of the speed of planets. We can see that in the patterns of cosmic microwave background radiation. So we have evidence that dark matter exists, but we know very little about its actual nature, its microscopic properties. That's why researchers have to look in all directions, and that makes the search very difficult, but also very exciting. And one day we will find something.
Dark matter must consist of particles that exert gravity, according to the theory. Furthermore, it interacts with normal matter, but through a very unusual force, the so-called weak force. It should therefore be possible to detect it, with the right method and the right detector. The search for the building blocks of this mysterious mass is ongoing, not only in particle accelerators, but also in the world's largest underground laboratory. The Laboratori Nazionali del Gran Sasso is located 1,400 meters below the Italian mountain massif Gran Sasso. The detectors are designed to capture so-called WIMPs, weakly interacting massive particles. Deep inside the rock, the laboratory is protected from distortions caused by cosmic radiation.
They haven't found anything so far. Now they're working to increase the sensitivity of the detector. It's possible that dark matter simply doesn't exist in this mass range and may have a higher mass. Or the signals might be so incredibly faint that the experiment needs to become even more sensitive. The challenge lies in the so-called background noise, which interferes with precise measurements. You have to get this noise down to zero, and that's what the physicists are trying to do.
The Italian underground lab is also home to the highly sensitive detectors of the CREST experiment. Here, ultra-pure transparent crystals of calcium tungstate are cooled down to almost minus 273 degrees Celsius. The hope is that a particle of dark matter will strike an atomic nucleus of the crystals and cause it to vibrate. This would minimally increase the temperature in the crystal. If this happens, a flash of light should be expected to flicker as well. That was the expectation. The experiment has been running since 2003, but even these highly sensitive and constantly upgraded detectors have yet to detect any particles of dark matter. The German electron synchrotron DESI in Hamburg is also searching for the particles that could constitute dark matter. Here, researchers are using an experimental array in an attempt to detect axion-like particles known as ALPS. Their light-through-the-wall experiment converts photons in a strong magnetic field into axions which can penetrate a barrier. On the other side of the barrier, they would then be converted back into photons and thus detected. To date, however, no ALPS have been detected. The search for light or heavy hypothetical particles such as ALPS, axions, or WIMPs is ongoing worldwide, but nothing has been found.
The search for these hypothetical particles, these WIMPs, has been going on for decades, but nothing has been found. It's simply frustrating. And that's why some physicists say that perhaps our thinking has reached a dead end. Maybe it's the other way around, that it's no longer about masses, and that the known masses simply have a different effect at great distances. If so, we would just need to adapt and modify Newton's theory of gravity to account for the observations. Then, we would need a modified Newtonian theory of gravity, modified Newtonian dynamics. And if that works, then we would have to adapt Einstein's general theory of relativity.
Could Einstein have been wrong? And are Isaac Newton's laws incomplete? Perhaps the universe doesn't need something like dark matter at all, a kind of glue that holds the galaxies together. There are researchers who say no, it doesn't. Gravitational force results from curved space, according to Einstein. Isaac Newton formulated the underlying laws of gravity back in the 17th century. And as some renowned scientists are suggesting, these Newtonian laws, which have been tested many times, would just need to be modified slightly.
Ultimately, you can develop any number of theories, but they always need to be anchored to a phenomenon. That means you have to find at least one experimental proof where, for example, Newton's law no longer applies. I'm an experimental physicist. What we are looking for right now, in many different ways, are new phenomena. If we discover new phenomena, then we can start to develop the theory. You can make speculations about new forces or changes in forces, but unless they're anchored to reality, they may not necessarily be useful.
The theory for adapting fundamental physical laws is called MOND, Modified Newtonian Dynamics. It states that the gravitational force acts differently at very low accelerations, such as in the outer regions of galaxies. If so, then dark matter would no longer be necessary to explain the effects. This theory was put forth by physicist Mordechai Milgrom back in the early 1980s.
The longer we search in vain, the more the occasional doubts grow. We may be hunting a phantom that we cannot actually find. Perhaps because the detectors we have simply aren't sensitive enough, for example. It's not as if nature necessarily has to be nice to us. It could simply be that these particles are so ghostly that we can't find them with our current detectors. Perhaps not for another 100 years or 500 years. That would be very disappointing. Naturally, doubts like these can arise from time to time. Nevertheless, there are many good arguments as to why we might succeed in detecting them, and that's why we have to remain patient.
Modern physics, the entirety of cosmology, every launch of a rocket and every movement of a space probe as it travels through our solar system, are based on the rules and laws established by Isaac Newton and Albert Einstein. To doubt these is almost sacrilegious within physics. But even if the MOND theory should prove untenable, the unsolved problem of dark matter is forcing physicists to think in new ways, perhaps even leading to a new understanding of physics.
Maybe Einstein overlooked something? Is his general theory of relativity incomplete, and thus Newton's theory of gravity as well? What is dark matter? Are they primordial black holes? Or perhaps just rogue invisible planets? Perhaps it's these hypothetical particles after all, which we just haven't yet been able to see. And what is dark energy? There are a few ideas, but we don't know exactly. Don't worry, the time will come, and I think we'll get an answer in the not-too-distant future. And until then, it remains very exciting indeed.
What are the fundamental laws of physics? How big is the universe? How did it come into being, and what is it made of? These are questions at the heart of cosmology. The study of the universe's origin and evolution is one of the most thrilling fields in natural science. It spans everything, from the tiniest subatomic particles to galactic superclusters, the largest known structures in the cosmos. And throughout it all, two mysterious forces seem to dominate: dark matter and dark energy. Together they make up the two greatest puzzles in physics today: Solving them would be nothing short of a breakthrough, one that would launch science into a new era, with humanity along for the ride.